Hello everyone, my name is Richard Russell. Along with Patrick Kavanagh and Michael Hewen, we're going to share with you some insights into how we delivered the design of the Western Sydney Airport bulk earthworks project. Patrick will share some of the challenges in modelling multiple stages of bulk earthworks, and Michael will provide insights into the design of the stormwater drainage. I will share with you how the verification process can be integrated into design development. But first, an introduction to the project. Why does Sydney need another airport? Demand for aviation services in the Sydney region is forecast to double over the next 20 years. Sydney Kingsford Smith Airport alone cannot handle those demands, even if its curfew is removed. A site at Badgerys Creek, 45 kilometres west of the Sydney CBD, was reserved for an airport about 30 years ago. The site is nearly 1,800 hectares of undulating terrain. It intersects two large creeks and a transmission line, and contains significant Aboriginal and European heritage. The bulk earthworks project was one of the first contracts for the airport construction and was awarded to CPB contractors and Acciona. An Arcadis and Aurecon joint venture developed the design. The project is well into construction, moving up to 1 million cubic metres of earth about every 2 weeks. When the airport opens in the mid-2020s, it will have a single 3.7 kilometre long runway and associated taxiways, aprons and aviation facilities. This will cater for about 5 million annual passengers, which is expected to grow to 10 million after about 5 years. The airport has been designed to be developed to meet demand. Additional taxiways can be added to increase capacity to about 37 million annual passengers. A second runway will further increase capacity to about 82 million annual passengers around 2063. This is about double the number of passengers through Sydney Kingsford Smith, pre-COVID obviously. It's hard to convey how vast this project is, but two key figures will help. 48 kilometres of stormwater pipe will be constructed, and 25 million cubic metres of earth will be moved, which Pat will talk about next.
Thanks, Richard, and g'day to all listening in. 12D Synergy was used to manage 12D model data. This gave great vision of data history and seamless data sharing with users around the globe. AAJV 12D model customization enabled consistency of data creation between JV partners and project-specific data sharing. AAJV 12D model manual helped with the implementation and management of data creation standardization, including information concerning stage, zone, surface naming conventions for projects, models, tins, and strings. The major challenge from a geometry perspective was the scale of the deliverable at hand. To produce 3 surfaces, finished surface level, design subgrade level, sandstone improvement level, for 4 design stages, bulk earthworks contract, 10, 37 and 82 million annual passengers. Total of over 50,000 strings, 2,000 super aligners and 380,000 points. Optimization of the earthworks volumes of such a large site, where a vertical change of 10 mil could result in 100,000 cubes of earthworks. This required much optioneering to achieve our solution, essentially warping of surfaces around geotechnical conditions whilst maintaining a compliant design. How do we automate the design updates, knowing that design would change horizontally and vertically many times over the project life to achieve the ideal solution? The models needed to be completely dynamic. Some of the processes we used to achieve this were: the ultimate design was created first. Traditionally, interim staging would come first. It was split into 4 zones, 4 12D model projects, in which team members worked closely adopting best methodologies to ensure consistency in the build process. The strings for the 3 surfaces were created and shared into a federated project where the information was combined and surfaces created. Approximately 50% of the ultimate design strings were duplicated, manipulated to form part of the interim stages. Additional stage-specific information was created inside the project to complete the stage designs. This is a general overview of the process. Fence the ultimate design strings to copy by using a closed superalignment. Fence the ultimate design strings to manipulate by using closed superalignment, and then translate the information to required depths. Create any strings that are specific to the stage by applying MTFs to superalignments. Any string information that is used in more than one stage is copied within one MTF. Remove copied strings when new strings are created by fencing out the data using MTF polygons or tin boundaries. And then we copy it to one model. Over 2,000 superalignments created using computator element method only, in which ensured alignment controls were fully dynamic and updates of controls were automated. Master controls of the airfield geometry, runways and taxiways were created in a separate project, then shared into zone-specific projects and referenced in zone-specific superalignments. These controls set the general levels and site layout. They were manipulated many times, approximately 150, for optioneering purposes to achieve the preferred geometric solution. This ensured a greater control of critical airfield design geometry, while allowing other team members to focus on content creation, facilitating fast optioneering. When referring to fillets in airfield design, we're referring to the pavement edge between taxiways in which follows the plane turn path. The complex horizontal and vertical geometry was created relative to taxiway master controls. So when the master controls were updated, the fillets were easily resolved and recalculated. Creating the finished surface strings was detailed in itself, although the subgrade and sandstone improvement strings also had its own nuances, in which would evolve over the project life, including different offsets and pavement interfaces depending on the geotechnical conditions of a particular area. Layers were created inside the MTF in which some of the finished surface strings were copied to. Then the specific interfaces were implemented to that layer and copied to a model. Gone are the days of the old boxing method. In addition, the use of alias, regions, comments made even the most complex MTFs understandable. The use of chains enabled automated recalculation of all objects created in the model, whilst maintaining a record and sequence of actions required. For example, if we updated the longitudinal grade of one runway, an overview of the general process for updating all models by using chains are as follows. Resolve all master airfield geometry superalignments, resolve all superalignments and recalculate all MTFs in 4 zones, federate the ultimate stage, self-checking assessments of surface slopes, pavement depths, etc. If the assessment passes, we move on. If not, we go back. Create stages BP, map 10, map 37 via data duplication and manipulation. Resolve all stage-related superalignments and recalculate all stage-related MTFs. More self-checking assessments. If it passes, we move on. If not, we go back. Federate BP, map 10 and map 37. Then the design review was run by Richard. If the assessment passes, we move on. If not, we go back. Then we'd run all 2D and 3D data outputs. Go grab a coffee while hundreds of outputs were processed. This ensured consistent data sharing in a timely manner. That's me. Now to Michael with the drainage challenge.
Thanks, Pat. So as you've just seen, the Western Sydney Airport is a pretty big and complex site with multiple stages. So there were plenty of challenges for drainage design and modeling as well. There were thousands of water strings for all the culverts and channels across different stages, permanent and temporary. We had, more than 10 sort of drainage engineers working on and reviewing the 12D drainage models all at the same time, which is a lot. And finally, we had to combine all our data to produce a single output per stage frequently. So in short, the biggest challenge to drainage in this project was really data management. How could we accurately keep track of all the different strings across the stages? How could we share data between so many users at once? And how are we going to aggregate and combine all this data in a very consistent and repeatable way? So I'm going to take you through some of the methods we used to sort of tackle these challenges. Let's start by taking a look at the staging, which was fairly similar to the geometry team. When the models are fully compiled, each stage is clearly identifiable with the different string color, sort of yellow to magenta here. And just like the geometry team, we actually modeled the ultimate stage first before we split them back into the interim stages, which is not conventional. And zooming in here, each string also had a pretty logical string naming convention to identify the different structures. This was a huge help to get schedules and quantities at the end. So for example, finding out how many pipes there were in a BEP stage, finding out how many head walls there were, all we needed to do was check the string names. And these were also accurately modeled in 3D, including all the channels, sizing and levels, so we could coordinate with the geometry team and also use them for hydraulic analysis afterwards. The actual design process is somewhat similar to the geometry process. We start off with the individual projects and our individual designers. We model all of the base or the permanent drainage structures first, and then we model all the temporary or like the stage specific extra models separately, and just share everything back into the federated project using master shares. And as you can see here, there's many different models and many different projects. So we use the project description in Synergy to keep track of all of this models so everyone could see the list at the same time. Once everything was shared in, we needed to develop and run a whole suite of chains. And these chains would create all our sharing models and all our export files. As you can see on the screen, there were heaps of them, all done automatically. The best part of all of this was the entire federation process took about 15 minutes. So we could run these chains every single day, and everyone in our team could see all the latest changes and talk to each other and fix all the problems on the go. This graphic here shows the key role the federated project played in one slide. So we funneled in all the data from the drainage designers, created this whole sort of platform that everyone else could view, the geometry, the structures, reviewers, clients even, and could even feed all this feedback sort of back to the drainage team quickly. As an added bonus as well, we used the federated project to add the final touches to all of our BIM outputs as part of the whole federation process. So I've shown the culvert head walls here and the attributes, and these will all automatically attribute at the end, automatically added at the end through some pretty long chains. And this was a huge time saver as well, because the drainage designers could focus on all the other things like the pipe sizes, the pipe levels, whether the channel sizing was right, and they didn't have to worry about all the different head wall sizes or even the attributes for the metadata or BIM requirements. And we could produce all of this in a very consistent and very repeatable method using all the chains that we developed. So by developing and implementing a pretty logical set of chains, procedures, and using a federated project to sum all our data together, we achieved some pretty good outcomes. We created really accurate models in each stage just by filtering and duplicating the right data. We had a really consistent and also almost live model by filtering and duplicating that we can share to our team daily. The whole federation process was quick. It only took 15 minutes and is fully automated. And it's basically saved us many, many hours in design and checking. And it's let our designers spend more of the time on the critical modeling and analysis work. That's it for me. I'll now hand it to Richard to talk about verification in 12D.
As mentioned before, airports are massive. It should have been subtitled to this presentation. Our traditional design verification and review tools such as long sections, cross sections and contour plots did not provide a quick way to identify problem areas. The geometric design requirements for an airport are complex to the uninitiated. Whilst the construction of runways, taxiways and aprons was not within our scope, we had to create a conforming design on which to model the earthworks and drainage. We needed a review process that provided quick feedback to the design team and documented evidence of conformance. I will share with you how we verified slopes, change in slope and the effect of settlement. To verify slopes, key feature strings from the federated model were copied for analysis. Sections were cut through strings and stored in separate models based on the design element. We then used slope range files to colour the string segments based on their slope. All of these processes were run from chains to provide a reliable and repeatable process. These models were shared with the designers who corrected the non-conformances. The same information was used to create PDF drawings as evidence of verification. The longitudinal feature strings for centre lines and edge lines, along with wheel path lines, were all analysed. The drawing sheets used were identical to the design drawings. The drawing content was managed by view favourites and a spreadsheet for the title block content. Problem areas were quickly identified and the design managers had the reassurance that areas were turning green each week. It also showed that it was impossible to be fully compliant in particular areas. The whole range of checks could be performed and documented in about 20 minutes. This meant that it could be run on a daily basis, even in the busiest times of the project. Slope range files were presented in a unique table style so that conformance of different features could be presented in a single plan. The PDF plans were included in design reports and used at design review sessions. Non-conforming areas were highlighted and reviewed in detail in the model. A conformance check that is unique to airports is a check for change in grade. This check has to be done for the runway and the runway strip, which is the area adjacent to the runway pavement. We created a 1 metre grid aligned with the runway. The y-axis of the grid ran along the runway and the z value was the design surface level. This will really show you how powerful grids or rasters are for analysing data. This grid was exported to Excel to calculate the change in gradient at each grid point along the runway. The percentage change in gradient was saved as the grid Z value. We then imported the grid back into 12D, triangulated it, and shaded the gradient values, or the tin Z value, with a height range file. The result of the change in slope analysis was presented on plans. These images are taken from a late stage in the design process, so many of the non-conformances have all been addressed. When you have a project with significant depths of fill, long-term settlement is going to be an issue. We needed to be sure that the runway and taxiways were not going to settle out of conformance. 12D already has tools that could be used to perform this check. Firstly, a 10 metre grid was created over the whole site. Using the create Z values from tin differences function, the level difference between the natural surface and the bulk earthworks was saved at each grid point. This was exported to Excel to calculate the predicted settlement at each point, based on parameters from the geotechnical engineers. We imported the grid back to 12D and triangulated it to make a settlement tin. Using the settlement function, the design strings analysed previously were settled, and the segment slope analysis rerun. Generally, this showed that conformance was maintained after long-term settlement. Some areas actually improved after settling. The plans produced to show the longitudinal slopes post-settlement used several presentation tricks, overlaying the height range colouring of the settlement tin with settlement contours, and view favourite files to control the plan view display settings and drawing order to ensure consistency when plotting. Several successes were realised from the verification processes we set up, including the design verification into design development workflow, allowed the design team to quickly correct non-conformances and focus on key problem areas. High quality presentation meant that the design check drawings could be included into design reports with no additional work. The process developed a high level of trust between the client's verifier and the design team.
Thanks, Richard. So you've just seen how the three of us and our team successfully used different parts of 12D to deliver a full-scale geometry design, drainage design, and verification on one of the biggest infrastructure projects in Australia. With the help of 12D Synergy and some ground rules for sharing, we successfully coordinated more than 20 designers working together on the same models remotely, without it turning into a huge mess. By taking advantage of chains throughout the delivery process and having an automation mindset, we've created a very consistent and streamlined methodology which saved countless hours of designing and checking. The biggest insight of all is that all the time we spent on data management strategizing and project setups was crucial for our overall success. Even when the pandemic hit in the middle of our major deliverables, we could stick to all the plans and processes we developed, transition quickly to working from home, and successfully deliver the Western Sydney Airport bulk earthworks detailed design. Thanks for listening, and that's the end of our presentation.